Dear students, we continue our discussion of matrix algebra. Today we discuss the concept of inverse of a matrix. Inverse of a matrix. The inverse of a matrix A denoted by A inverse, the inverse of a matrix A denoted as A inverse is defined only if A is a square matrix. A is a square matrix, in which case the inverse of A, that is A inverse, satisfy the condition A inverse equal to A inverse A equal to I. If it exists, satisfy the condition A inverse equals A inverse A equals I. We will explain more about inverse. Let us first see what are the properties. Not every square matrix has an inverse. Squareness is only a necessary condition for the existence of inverse. Not every square matrix has an inverse. Squareness is only a necessary condition for the existence of inverse. It is not a sufficient condition. Now, if a square matrix has an inverse, then the matrix is said to be non-singular. Non-singular. Not every square matrix has an inverse. Squareness is only a necessary condition for the existence of inverse. It is not a sufficient condition. We will explain sufficient condition later. Now, if a square matrix has an inverse, we will say that A is non-singular. On the other hand, if the square matrix has no inverse, we will say that A is singular. So, if the inverse of a matrix exists, it is non-singular, otherwise it is singular. Then, the second property is, if A inverse exists, then A can be regarded as the inverse of A inverse, just as A inverse is the inverse of A. If A inverse exists, A is the inverse of A inverse, just as A inverse is the inverse of A. The third property, if A is an n by n matrix, then A inverse is also equal to n by n. Then only this condition will be satisfied. If A is n by n, remember this, inverse exists only for square matrices. If A has the order n by n, A inverse also has the order n by n. Then only the condition A inverse equals A inverse A equal I will be satisfied. Now let us see what are some of the other properties. Now, in addition to this, if A and B are two matrices, AB inverse is equal to B inverse A inverse. Then A inverse transpose is equal to A transpose inverse. Then if the inverse of a matrix exists, it is unique. It is unique. If the inverse exists, then inverse is unique. Then alpha A inverse, where alpha is a constant, is equal to 1 by alpha into A inverse. Then A inverse is equal to A. Then A inverse transpose is equal to I transpose is equal to I. Then A inverse is equal to I. These are some of the properties of inverse. Some of the properties of inverse. Inverse exists only for square matrices. Squareness is only a necessary condition. Even if a matrix is a square matrix, it is not necessary that its inverse exists. If inverse exists, it is known as non-singular. Otherwise, it is known as singular. Then, if A is n by n, A inverse is also n by n, then only we can post-multiply or pre-multiply A with the A inverse. Then AB inverse is B inverse A inverse. Then these properties be kept in mind. We will use some of these properties when we present econometric models using matrix algebra. Now let us see how we actually find out the inverse of a matrix. If A is a square matrix, its inverse is written as A inverse, and A inverse is equal to 1 by determinant of A into adjoint of. Determinant is a concept which we will see in the next class. A inverse is equal to 1 by determinant of A into adjoint of A, also known as adjugate of A. Now let us see what are the steps. The first step is find the determinant of A. First step is find the determinant of A, written like this, determinant of A. And if the determinant is not equal to 0, if the determinant is equal to 0, A inverse will not exist. A inverse will not exist. We have defined matrix A as non-singular if its inverse exists. In some cases, you will also see the usage that for a square matrix, if the determinant is not equal to 0, for a square matrix, if the determinant is not equal to 0, it is non-singular. Otherwise, it is singular. And both statements are same in the case of a square matrix. That we will see. So that is the first step. The second step is replace each element Aij by its cofactor. Each element Aij by its cofactor. Then the third step is transpose the cofactor matrix. Cofactor matrix. So each element is replaced by its cofactor and obtain cofactor matrix. Then transpose the cofactor matrix to obtain the adjoint matrix. Then divide each element of the adjoint matrix by determinant of A. These are the steps. So first determinant, if it is not equal to 0, each element of A is replaced by its cofactor, obtain the cofactor matrix. Transpose of the cofactor matrix is the adjoint matrix. Then each element of the adjoint matrix is divided by determinant, that is A inverse. To obtain this cofactor, the first step is to obtain the minor. Now, what is a minor? If the ith row and jth column of an n by n matrix A is deleted, the determinant of the resulting submatrix is called the minor of Aij. Let us see how it is. And it is denoted by Mij. Let the matrix is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, a 3 by 3 matrix. Then the minor of the ith row and jth column, say the first one, A11, is, if we delete this ith row and that is the first row and the first column, you will get M11 as equal to determinant of A22, A23, A32, A33. This is equal to A22, A33 minus A32, A23. Determinant we will see in the next session. So this is minor. So similarly, the minor of this element is the determinant of this. Minor of this element is the determinant of this. Similarly, minor of this is this like that. Now, what is cofactor? Cofactor is nothing but the signed minor, and it is denoted by Cij. Cij is equal to minus 1 raised to I plus j Mij. So cofactor is signed minor. The rule is minus 1 raised to I plus j into what is the minor of the element on the ith row and jth column. Now if I plus j is even, such a square, it will be positive. If I plus j is odd, it will be negative, like that. Then that is cofactor. Now what is cofactor matrix? Cofactor matrix is, we replace each element of the matrix A with its cofactors, such as C11, C12, C13, C21, C22, C23, C31, C32, C33. Then that is the cofactor matrix. Then what is adjoint matrix? the transpose of the cofactor matrix. That means C11, C12, C13, C21, C22, C23, C31, C32, C33. This is the adjoint matrix. So this is the process by which we find out the inverse. Determinant not equal to 0, then Aij replaced by, so on to obtain the cofactor matrix, take its transpose. The first step is calculate all the minors. That is the determinant of the elements obtained after deleting that specific row and column. Then signed minor is cofactor. Transpose of the cofactor matrix is nothing but the adjoint matrix. Let me consider a simple example. I write it very quickly. You practiced A is equal to 1, 3, 4, 1, 2, 1, 2, 4, 5. Then matrix of minors is Mij is equal to 2 into 5, 10, minus 4 into 1, 4. That is 6. Likewise, 1 into 5, 5, minus 2, 3, 0, minus 1, minus 3, minus 2, minus 5, minus 3, minus 1. Then Cij, cofactor matrix, that is signed minor. 6 minus 1 raised to Ij 1 plus 1, 2. That is 1 into 6, 6 itself. This becomes minus 3, 0, 1, minus 3, 2, minus 5, 3, minus 1. Then adjoint matrix is the transpose of the cofactor matrix 6 minus 3, 0, 1 minus 3, 2, minus 5, 3, minus 1. And the determinant of A is equal to 1 into 2 into 5, 10 minus 4. That is 6 plus 3 into minus 3 plus 4 into calculation of the determinant we will see in the next session. 4 minus 4 is equal to, that is 0, equal to minus 3. So A inverse is equal to 1 by minus 3 into 6, 1, minus 5, minus 3, minus 3, 0, 0, 3, minus 1. That is A inverse. It's a solution. That is, we divide each entry by the determinant. Minus 2, minus 1 by 3, 1, 2 by 3, 1, 1, minus 1, 0, minus 2 by 3, 1 by 3. That is inverse matrix. Inverse is, if this is A, its inverse is this. And if you multiply this A with the A inverse, you will get I as the result. And you may wonder why we calculate the inverse of a matrix. As we will see later, for the solution of a system of linear equations, matrix algebra is very handy. For that, we have to find out the values of the unknowns in a system of equations. We have to invert the matrix. So matrix inversion is required to find out the values of unknowns in a system of equations, that we will see with an example. And inverse exists if and only if the matrix is a square matrix. But squareness is not enough. Another condition is also there that we will see in the next section. So inverse is calculated as 1 by determinant of the matrix into adjoint of the matrix. The procedure for calculating this is given in all the basic textbooks I have suggested earlier. I recommend that you practice this procedure. Even though it is not required in econometrics, we will not use numerical calculations in econometrics. And also, softwares will do all the work for us. But a knowledge of matrix inversion will be useful for clarity of presentation, thought, etc.